Okay. Hi, Nate. I'm gonna introduce you and then mute myself. And if we have questions, I'm gonna moderate. Okay. All set? Thank you. Hi, everyone. Let's start the afternoon session. We have Nate Foster as the first speaker. He's in Switzerland for now, and he's gonna come to Korea like tomorrow, I guess. And meanwhile, we are gonna welcome him remotely. Could you please give him big hands and he can start.
Great. Yeah, sorry that I can't be there, but I will be at PLDI starting tomorrow. I want to tell you about some work that we've been doing on using real-world programming languages specification to reduce the cost of formally verifying some systems. And this is joint work with collaborators at EPFL and ETH Zurich, led by an exceptional PhD student, Charlie Cast. So we've been interested in building and verifying hypervisors, which are really the foundation of many modern systems. They make it possible to virtualize physical resources and share them amongst multiple applications or even different tenants who don't trust each other. And because of where they sit in the system architecture at the very lowest layer, it's really important that they be correct, because a bug in a hypervisor can really subvert a guarantee that you might have proved higher up the stack in the application, in the compiler, and even in the OS. So Charlie and others have been building a new hypervisor called Morales, which the talk is not about. But just to give you a little taste, it's a hypervisor that, like others, allows you to run multiple VMs or applications on the same machine, but it also virtualizes the firmware. And this is nice because it reduces the trusted computing base, because the firmware is a whole bunch of code that normally runs with raw access to the machine. So like any complex piece of software, hypervisors are hard to build. And it's not that hypervisors are this kind of deeply mysterious thing. They're basically a kind of interpreter. But the main difficulty lies that they have to deal with the full scale and complexity of modern hardware. And if you look at the lengths of the specifications for ISAs, they often run to hundreds or even thousands or tens of thousands of pages. So they're pretty complicated. Distilling it down to its essence, what would it mean to verify a hypervisor? What kind of properties would we want? We'll get into more formal definitions in a little bit, but at a high level, there's basically two key responsibilities that a hypervisor has. It has to somehow emulate the hardware, so it allows the VMs and apps to execute against a virtual interface that then gets emulated against the actual physical hardware. But it also has to configure the hardware. So there's all kinds of state that's involved in things like memory protection, sometimes clearing out state when you switch from one application to another, and so on. And so all of this is done through certain instructions that manipulate that state. And doing that configuration correctly is pretty subtle. So we'd like to verify these hypervisors. It's hard because of the complexity, but it's also hard because, if you think about doing this just from scratch in some kind of tool, you'd have to do a lot of work. You'd have to write a spec, and not just for the hypervisor, but probably for the instruction set. And then you'd have to somehow do a proof. And if you were doing this in the context of an ongoing development, you'd have, of course, to maintain that proof. So the question we asked in this work is, how far could we get being as lazy as possible? So could we really automate most of the work involved with verifying these core correctness properties for a hypervisor? And in particular, can we mostly skip writing the spec and even the proof? And the answer is yes, we can. And it's based on two key observations. First is that while hypervisors are complex largely due to the scale and complexity of these instruction sets, they have a lot of structure. They're basically a kind of interpreter that repeatedly fetches or dispatches on the next instruction, and then decides what to do, whether just to emulate that instruction, execute it natively, or possibly do some configuration of the hardware. And so we can harness this structure in our tool. We're not, even though hypervisors might be tens of thousands of lines of code, the verification can be broken down into these smaller chunks, making sure that each instruction is correct. And second, although again, most of the complexity comes from the hardware, we can leverage all the great work that's been going on in this community. And in particular, Peter's group at Cambridge has been developing this system called SAIL, which is a DSL for writing down specifications of instruction sets. And the SAIL community by now maintains specs for several real-world ISAs, in particular RISC-V and ARM. And so we can leverage all this great work to let us basically start from a specification of the hardware that Peter and the community have built, and that greatly reduces the load for our work. Okay, so I don't have a whole lot of time, but I want to just kind of take you through a tour of the system that we built and a little bit of the insights. So I'll start by reviewing some sort of classic ideas in hypervisor correctness. Then we'll go into some of the details of how this plays out in a hypervisor like Morales, so how we emulate instructions and how we execute instructions faithfully. And then I'll close with kind of a case study of some of the experiences we had applying this to Morales and some of the bugs we found. Okay, so I gave you kind of informal definitions, but let's get a little more precise. So what do we mean by hypervisor correctness? Well, let me tell you a little more about the architecture. So the hypervisor, we call it colorfully the hardware burger. I guess it's kind of a vegan burger because it just has these two buns that you see in yellow and some kind of lettuce in the middle. But essentially, you have this piece of software that sits between a virtual interface to hardware, and it's important that this be a hardware interface because your virtual machines want to pretend that they're running against a real machine. And then at the lower layer, of course, you have the physical or host hardware interface, which is the one that's natively supported by the ISA. It's a little more complicated than that because, as I mentioned, there's in many of the instructions, their semantics depends on some state, which is not state that we tend to think about most of the time as programmers, but it's very important at the low levels of the system. And I'm just going to call these configs. So these configs, again, do things like configure the memory protection, certain registers or other state that controls memory protection, and other features. And here, the configuration is going to live both in some cases at the virtual level and, of course, at the physical level, which I'll call the platform config. So what do we mean for hypervisor to be correct? Well, basically, we'd like it to be the case that if we take this hardware burger and then on top of it, we decide to run, say, a virtual machine, that this should be equivalent to running on some kind of reference machine where there's no hypervisor, there's no virtual interface, and we just run the VM natively. So formally, we'd like the VM to be a simulation of some reference machine. And this idea of simulation, which is very familiar in our community, was actually used in a classic paper in the operating systems community by Popek and Goldberg. And they were interested in formalizing conditions under which an instruction set could be virtualizable in the mid-70s. But we can also take their design as giving us basically a roadmap for doing formal verification of hypervisors. At the time, they were working in the 70s when it actually wasn't the case that every hardware architecture was virtualizable. So sometimes there were instructions that essentially, you couldn't expose to the VM because they would do things that you couldn't intercede and correctly emulate. But mostly due to the influence of this paper, most modern architectures are virtualizable. And as a result, you can build hypervisors that use a strategy that's often known as trap and emulate. And the basic idea is that we're going to split the instructions in the ISA into two categories. There's going to be unprivileged instructions, and these are going to be the ones that are going to be safe to execute basically directly on hardware. And in fact, we'll want to do that because this is a difference between the OS and the PL community. While from a sort of functional correctness perspective, it doesn't really matter if we emulate an instruction by doing something behind the scenes or allowing it to execute directly. But if you're in an operating system, you care about speed. And so in the original Popek and Goldberg formulation, they wanted to have certain instructions that actually just do run natively on hardware. And they wanted to identify when it's safe to do that. So those would be the unprivileged instructions. The privileged instructions are the ones where it would not be safe to let them run natively. And so instead, we're going to have them trap, and then the hypervisor will be able to intervene and do whatever it has to do to ensure that the whole system continues to execute correctly. Okay, so sorry, missed one slide. So in the unprivileged instructions, we get a very simple picture where the host and reference machine are basically doing the same thing. Whereas with the privileged instructions, the host machine, which is what I'll call the whole complex of the virtual interface, the VM running on top, the hypervisor, and the host machine, it may take many steps as the hypervisor configures the underlying host machine to do its work. Okay, and of course we want these things to be in some kind of simulation relation, even when the host machine has done this more complicated sequence of steps. Okay, so we call these two categories of instructions and their correctness properties faithful emulation and faithful execution. So I'll do them in the reverse order as what I just described. So for faithful emulation, we want it to be the case that the hypervisor can accurately emulate the privileged instructions, just capturing the picture I already showed you. So the reference machine takes a single step, and then on the host machine, that privileged instruction is eventually emulated. But in the middle, we may take several steps, including manipulating some of this state that I've referenced several times. Here's another way to see it. For all states of the system, that's the S you see here. And for all privileged instruction, that's the I you see in purple on the top. If we're running the two systems, on the left you see, say, the version with the hypervisor. On the right you see the reference machine, which here is just, say, RISC-V. We'd like the hypervisor to, when both of these executions have terminated for this instruction, we'd like them to end up in an equivalent state. Okay, and then faithful execution is just the other picture, where for the unprivileged instructions, it's just directly executing. And again, we'd like that to be indistinguishable, or also equivalent with the simulation of the reference machine. This seems kind of totally straightforward, but I just want to remind you that it's a little bit more subtle, because the behavior of many instructions will depend on this privileged state. And I've referenced this several times, so I'm going to drill down and show you a little more detail how that works. So this privileged state exists at both layers. So we have privileged state that's at the virtual level, we have privileged state that's at the host level. Again, we want it to be the case that as the hypervisor is configuring and managing this privileged state for the host system, somehow this whole picture still gives us a simulation. So to trace this through, here we have, again, in the middle, we have our initial state, we have the unprivileged instruction, and the hypervisor up here will have configured the host state. This is for the underlying host hardware, and it also has access to the privileged state for the virtual machine up here. And we want it to be the case that no matter which of these two paths you followed, so here is the reference machine where we just have the virtual program running on just a regular in a regular RISC-V context with this privileged state, the final state that it produces, again, should be equivalent to what happens where the hypervisor is actually configuring the host state, possibly taking several steps, and then running that through the host machine. Okay, so that's a little bit about hypervisor correctness and how these conditions kind of get translated to a realistic stack. With the few minutes I have remaining, I want to tell you a little bit about experiences building verification for Morales. So I already showed you a small version of this picture, but Morales is a new hypervisor being built by Charlie and others at EPFL. And it has much of the same structure as classic hypervisors. So it sits at the lowest, or the highest level, rather, of privilege, called M mode for RISC-V. This is machine mode. And then it allows you to run different pieces of software at less privileged modes. So the OS running at S mode and the applications running at U mode. And again, I'm not going to focus on this talk, but one of Charlie's interests and others is to be able to actually virtualize the firmware, which is a bunch of code that runs on any system. And they've actually created a new mode for firmware that they can boot real systems running Linux on RISC-V with the firmware all being virtualized. So Morales is a big system. Charlie and others have been working on it for several years. And They've experienced a number of pain points in development. They have to emulate over 80 privileged registers. They have to deal with complex conditions involving interrupts, and they really want to ensure that there's strong properties like memory isolation. So during execution, during development, as usual with writing low-level software, they were building the system, they were trying to get things to run, fixing tests. This was quite painful. And in this project, we were actually able to verify the core logic of all three of these pieces of Morales using this lightweight technique. So how did we do this? Well, again, the key insight is that we leveraged the work on Sail. So Morales is written in Rust. Sail provides these specifications for RISC-V. And Charlie wrote a simple Sail to Rust backend that generates Rust RISC-V model. So now we have our hypervisor written in Rust, and we have essentially the reference semantics for the ISA that we can also just run in Rust or analyze in Rust. And then using the Connie verifier, we're able to now apply this to our conditions, which come from this classic Popek and Goldberg work, and these Rust artifacts to check that they have the properties we want. So let me show you what this looks like. This is a piece of code taken directly from the Morales code base, completely unmodified. And it's an example of how we would verify a single instruction. In this case, it's the mret instruction, which returns to either S or U mode from M mode. M mode is the machine mode, which is the lowest, the highest level of privilege at the lowest level, and we're going back up. And so just stepping you through this, essentially the first line here creates what we call a symbolic context. This encodes an arbitrary CPU state where all of the registers have, they have arbitrary values, they have to satisfy some validity conditions, and we also have the instruction that we're interested in analyzing here. And then on the next two lines, we have basically the two executions that we want to relate. So we have the Morales execution. We just call out to here the Morales, and we pass the appropriate state and context for Morales. And then down here, we have the corresponding Sail code, where we just directly execute that code. Sorry, don't directly execute, emulate that code. And after doing this, we now have the two states that you see here on the picture. And then we essentially want to check that these things are equivalent. There's a small subtlety, which is that Morales and Sail use slightly different data structures to represent the CPU state. So there's a little conversion function, Sail to Morales, that maps the Sail state back into the Morales representation, and then we can check that these things are equal. Okay, so this is basically the amount of specification that we have to do. We have to do this for each instruction, but it's pretty boilerplate. And in fact, we have a version where you can do this for a symbolic instruction. And the main trade-off there is that you write a smaller spec, but the verification takes longer because now even the instruction is symbolic, so the verifier takes longer. It takes about 2 hours in our tool. Okay, so using this style of specification instrumentation, we're able to find to verify all the instructions that Morales handles, including all those 84 privileged registers and everything else. In the course of doing this, Charlie found over 21 bugs, and some of these are, what you might call functional correctness bugs. Here's a listing. I won't bother to pronounce it because I think I don't have enough time. And there's also some bugs that lead to crashes or, basically escape some of the isolation protections that the hypervisor is supposed to verify. So these are particularly bad bugs for a hypervisor. Let me show you just a few of these. So here's a snippet of code that's involved in memory protection. So it's the code that transforms the virtual machine's physical memory protection into the physical memory protection. And here the bug that existed in the code base was that the Morales forgot to basically mask out the lock bit for when mapping the virtual physical memory protection bits into the host one. And so as a result, the guest is able to control a particular bit, which is called the physical lock bit. And when this bit is set, then the entry can no longer be changed, and the memory protection basically is the same as in end mode. So in other words, the guest would be able to change the memory protection of the host arbitrarily. This is pretty bad as a bug because that's not something that a VM should be allowed to do. And you can see in green, here's the fix. The fix was basically a very, a low-level thing where we just mask off the bits differently so that the VMs can't do that. Here's another bug. This involves a certain load instruction. There's some code that decodes the compressed load instructions. These are certain instructions which sometimes need to be emulated in Morales. And here the decoding, which you can see is kind of, fiddly masking and shifting and stuff, had an off by one error in the computation of the immediate for the load. You can see that there's a 3 in the buggy code and a 4 in the corrected code. So, you have to understand the details of how these compressed loads are encoded to know what this bug is from. But basically, it's the kind of code you could easily have in writing low-level code. And this doesn't, break isolation like the previous one. It doesn't directly crash the guest VM, but it can cause memory corruption or, in some cases, device misconfiguration. This isn't my experience, but Charlie reports that this is the kind of bug that is really hard to locate when you have kind of a first prototype and you're trying to run VMs on it, and you have to drop down into the debugger. You have to find a state and execution that gets you all the way to this line of code, and then maybe you can discover that this 3 should have been a 4. But with our verifier, this just fell out pretty much immediately. So when verifying the Popek and Goldberg conditions for this kind of compressed load and store, we immediately see the difference. We get an error trace, and then can go fix it. Okay, and just one more bug. This one is maybe not so interesting from it's kind of more of the same, but it shows how lightweight verification can be useful in the course of doing a development. So the way that Charlie built Morales is he started with a really minimal set of RISC-V, and in particular, RISC-V has all these extensions. And so he started with a minimal set just to get things working, and then he progressively added more. But it turns out that some of the extensions can actually change the behavior of certain instructions and state-like registers. So in other words, every time he added a new RISC-V extension, he needed to go back and basically redo all the verification or all the reasoning he had done to see if the new extension somehow changed the behavior of things he'd already implemented and validated. So here, in this particular example, there's some registers called the MEPC. They stand for Memory Exception Program Counter. Usually, the address that's stored in this particular register has data that's aligned to 4 bytes, but with there's a certain compressed extension, then the alignment is reduced to 2 bytes. So if this C extension is enabled, then you have to use a different mask, or you just get the wrong behavior. So again, this was kind of the kind of thing that was painful when just working without any kind of validation. But with our lightweight verification, add an extension, you discover that some instructions need to change, you get errors, and you go fix them. So it's really been help Charlie to accelerate his development of Morales. Okay, so I think I'm right at time, so I'll stop there. Again, this is not a talk about how to build formal specifications of real-world languages, but I hope it gave you a taste that these things can have amazing impact for downstream users. And in particular here, we basically did a case study of taking SAIL specifications of RISC-V, taking an off-the-shelf verifier in Connie, and using it to verify at pretty low cost a large complex system, namely the Morales hypervisor. So I think this shows that the work this community is doing, which is often focused on the mechanics of how we specify languages and how do we get them adopted and what are the tricky mathematical things we need from specification frameworks, like that's all great stuff. But we do have users, and I think that we can have an amazing impact on not just programming languages, but other systems if we continue on the path that we're following. Okay, so I'll stop there, and I don't exactly know how questions work, but maybe the room can unmute and take questions, or I do it on Discord. Just let me know.
Awesome. Do we have any question? Or yeah, please. So, Nate, I will take only one question from Ralph, and then we are going to move on. And if you have more questions, then you can grab him tomorrow. Okay.
Okay.
Now I have to decide which of how many questions I'm going to ask now. Yeah, thanks, Nate, for the great talk. I was wondering if you could say a bit more about the TCB of the result. Maybe on kind of two axes I'm thinking about here. One is Kani isn't a full verifier, right? It's a bounded verifier, in my understanding. So there is some like potential, I don't know, maybe there are just no unbounded loops in a hardware emulator for other reasons, so that maybe doesn't hurt you or something. And then the other thing is you mentioned something about when you create a symbolic state, there are some constraints on it, which sounds like some sort of invariant, which ideally someone would prove that it's globally maintained everywhere or something like that. Is this assumed, or is it also part of the proof? And what other things could there be in the TCP that like if we would be maybe a possible gap here to like a full-fledged formal rock proof or something?
Yeah, great question. I'll just say, a completely formalized or mechanized, end-to-end proof was definitely not a goal of this work. So this is very much, adopting sort of the more pragmatic lens of the systems community and saying, can we use all these things to build a tool that gives us some assurance, but we're not trying to squeeze out the last the last pieces of the TCP. So you're absolutely right that there are pieces that are trusted or places where there may be incompleteness due to, say, limitations of Kani. Having said that, I think that these choices made in this project are very reasonable. So first, with respect to Kani's limitations, we're not verifying start to finish all of Morales. So there's a fair amount of instrumentation and basically guiding Kani to just verify the individual steps of the instructions. We have played a little bit with doing a more end-to-end thing, but as I briefly hinted at, that takes a lot longer. So we've had more experience with basically guiding it to verify these relatively small terminating snippets of code where the fact that Kani's a bounded model checker, basically doesn't cost us anything. Your second question was about what was the second part of the question? Can you just repeat it really quickly? I'm sorry.
You mentioned there's some like invariant-like constraints on the symbolic state you emit,
yes.
And like who ensures that those are actually true?
Yes. So there's other parts of the modeling of the system that I think you could connect these more closely to things like the sales spec, but for now, they're basically trusted. So the setting up of the context, that code needs to be right, or the whole model is basically wrong. And I've not thought deeply about how to remove that piece of trusted code. It's not very complicated, but you're right that it could be a place where a simple error about these invariants could undermine some of the guarantees.
Okay, with that, Nate, safe travel and see you tomorrow.
Hey, see you all tomorrow. Bye.
Bye.